Hello class, today we're going to go ahead and look at section 8.3, graphing rational functions. Before we go ahead and dive into actually graphing rational functions though, let's go ahead and look at the functions that we have already graphed this year. The first one is our linear equation. Notice that it is a line, and notice in the word linear, there is the word line. Typically when we think of linear, we think of y equals mx plus b. So the biggest thing in order to notice is that to have a linear, you have an x to the first term or just x. Okay. The other function that we've looked at this year is a quadratic. We had y equals, and this was our standard form, ax squared plus bx plus c. And if we look again, my highest variable with an exponent is x squared. So when we have a quadratic, it's x squared. Remember, it has that U-shaped, it's what we call a parabola. The next one we're going to look at is a square root function. We actually just got done graphing the square root function. Biggest thing to remember is that to have a square root function, you're going to have the square root of x or whatever may be underneath it. And just remember, that's the same as x to the 1/2 power. Okay, so just refresh. Linear is x to the first, quadratic is x to the second, and square root would be x to the 1/2 power. Okay, a few other polynomials that we have looked at are the following. Okay, and remember we looked at the different number of degrees. So this one, since it's going in opposite directions, entering and leaving on the opposite side, it's an odd function. Okay, it's an odd degree. And then to actually figure out the degrees, you count the number of turns. So there's one turn, here's another turn, so that's 2, and then we add 1 to that. So 2 plus 1 is 3. So this would be an x to the third polynomial, a degree of 3. The next one, we'd have 1 turn, 2 turn, 3. 3 plus 1, is 4, so I would have x to the fourth. So this is an x to the fourth polynomial. And then my last one, I have a turn here and here. There's 4 changes in directions or turns, and 4 plus 1 is 5, so this would be an x to the fifth polynomial. Okay. So we're going to go ahead now and look at, well, what is a rational function? And the way we're going to do that is we're going to start looking at an example. So a group of students want to get their favorite teacher, Mr. Domingos, a birthday gift. They plan to get him a gift certificate for a weekend package at a lodge in a state park. The certificate costs $150. If C represents the cost for each student and S represents the number of students, then, well, we want to come up with an equation for this. Well, it costs $150. How would you figure out how much it costs per student? One way I would think is just about the labels. Want to know the total cost, okay, divided by students, because it's cost per students. So my total cost of the gift certificate is $150 divided by the number of students, which they are saying is S. So the cost per student is 150 divided by S. Okay. So in this case, if I have one student that's going to buy, I would take 150 divided by 1. That means that one student's going to pay 150. If we have 25 students, I would take 150 divided by 25. That would give me $6 per student. So as you notice, okay, this is going to go and it's going to get cheaper the more students that contribute. Okay, if you have 150 students, they're each going to pay $1. Another thing to notice about this graph is this is a part of a rational function. Okay, because I have, a fraction here, and so the one thing to notice is this is going to get really, really, really close to the y-axis, but it's never going to touch. Same thing with down here. It's going to get really, really close to my x-axis, but it's never going to touch. Okay, so something to keep in mind. It's getting really close, but it will never touch. So let's just go ahead and talk about, well, what is a rational function? So a rational function is a ratio of two polynomials. Okay, so if I have f of x is equal to a polynomial over a polynomial, then that is a rational function. Okay, it has to have that ratio. So we have some examples here. We have f of x and g of x and h of x. These are all examples of rational functions. We have a polynomial in the numerator and the denominator, makes it rational. Okay. The next thing we're going to take a look at is continuity. Okay. For something to be continuous or to have continuity, that means that you will not have any breaks. Okay, it means you can draw the graph without picking up your pencil. Okay. Okay, so the graphs of rational functions may have breaks in continuity. So if you have a break, there's a break in the continuity. But to be continuous or to have continuity, it means I can draw a function and never pick up my pencil. Essentially, you can draw a parabola and never pick up your pencil. You could draw a linear function and I would never pick up my pencil. Okay. If a break occurs, okay, at a value, it's excluded from the domain. And we're going to talk about where these breaks would occur. Okay. So let's just use the examples from above. Where would a break occur here? So if we're looking at f of x, there's going to be a break at, well, I would look at my denominator. We all know you cannot divide by 0. So what would make my denominator 0? Well, if x equals -3. Because -3 plus 3 is 0, you can't divide by 0. So that would cause a break. It is also what we would call a vertical asymptote. Okay, that's a vertical asymptote. Let's go ahead and look at g of x. Does g of x have a vertical asymptote? Yes, it does. If I look at my denominator and I would think, well, x minus 6, where would that equal 0? If I solve it, it's when x is equal to 6. So once again, there's a vertical asymptote at g of x. Then if I look at my last example, okay, it's h of x. I'm going to write down here. You should have room, hopefully, on your note sheet. This is not supposed to be equal. Here. H of x. I look at this, and if you look at my numerator and my denominator, those x plus 4s will cancel. Okay? If something like that cancels, there's what we call a hole in the graph, or a break in the graph. And it's where those two would equal 0. So if I plug in -4, so there's a hole at x equals -4. There is also a vertical asymptote, and I'm going to label that VA. And that's going to be from this x minus 1. So where would that equal 0? Well, where does x minus 1 equal 0? It's when x is equal to 1. So x equals 1, there's a vertical asymptote. The next thing we're going to go ahead and look at is vertical asymptotes. Okay, it's a line that the graph of a function approaches but never touches due to domain restrictions. The biggest thing with those domain restrictions is that they're coming from the denominator, where the denominator is equal to 0. Okay, so for this problem, we have f of x, and they give us the function. It's x over x minus 3. So my vertical asymptote is going to come from my denominator. If I have x minus 3 equals 0, my horizontal asymptote is at, my vertical asymptote is at x equals 3. And usually on our graph, the way we draw that is with a dashed line, okay, and there is my vertical asymptote. And the last thing we're going to talk about here is our point discontinuity, or a hole in the graph. Okay, so I've already talked about holes, but here they are again. Holes occur when you have a value excluded from the domain, but cancels out when the function is simplified. So if you look at the function for the example we're given here, x plus 2's, those are going to cancel out. So I would say, well, what's going to make that 0? So I would have x plus 2 is equal to 0. So at x equals -2, that is where there is a hole. Okay, and the way you show that on the graph is with an open circle. Okay, so there's a hole there. And if those cancel out, there is no vertical asymptote. So that's my hole in my graph. Important, throughout all these problems, just continue to keep in mind that you can't have a denominator of 0. Okay? No denominator in a rational function can be 0 because division by 0 is not defined. If you ever forget, if you can take a number divided by 0, try it on your calculator. It's either going to say error, domain error, or give you a thing showing that you can't do it. Okay? And then also, if you're not sure, you could do 0 divided by 5. This will, on your calculator, say 0. So if you're not sure which way it is, check on your calculator. Use that tool to help you out. Let's go ahead and look at an example. It says determine the equations of any vertical asymptotes and the x values for any holes in the graph. Okay. Well, what you need to do, we have some steps down below that could help. Factor both the numerator and denominator if possible. So let's start with that. My numerator is a difference of perfect squares. So it's x minus 1, x plus 1, all over my denominator. What multiplies to 5 but adds to negative 6? Well, 5 times 1, to get to negative 6, they would both have to be negative. Okay, now I can go ahead and look at it. Is anything going to cancel? X minus 1s will cancel. So I would set it equal to 0 and solve. So that means that x equals 1, there is a hole. Okay. Now let's go ahead and see if there's any vertical asymptotes. This is my last piece in there, so I would have x minus 5 equals 0. So at x equals 5, there is a vertical asymptote. Okay, so there's my hole and my vertical asymptote. Example 2, same thing. We want to find any holes or any vertical asymptotes. So start by factoring. Multiplies to 8, but adds to 2. So 4 and 2, both positive. And then my denominator is a difference of perfect squares, so it's x, and then the square root of 16 is 4. Then there's always a positive and a negative. And then I would notice my x plus 4s will cancel. So then when they cancel out, okay, maybe I'll write out a little note. X plus 4, when they cancel out, canceled, canceled out. So if they cancel out at x plus 4 equals 0, I solve this. So at x equals negative 4, there is a hole. Okay. And the other value is for my denominator. Okay, we have an x minus 4, so I would set that piece equal to 0. This is my vertical asymptote. Example 3. Moving on to this one. Once again, we always start out by factoring difference of perfect squares, so x plus 2, x minus 2, all over. Now I would have to say what multiplies to 6 but adds to 5. 2 times 3 multiplies to 6, and they add to 5. Now does anything cancel? X plus 2's will cancel. So I would solve this piece, so x equals negative 2, that is a hole. And then the rest comes from the denominator for my vertical asymptote. X plus 3 equals 0, so at x equals negative 3, that is my vertical asymptote. Okay. We are going to go ahead and stop part 1 of the video with example 3. When we come back, I'm going to do examples 4 through 7, and I highly recommend that you get your graphing calculator out and ready, because that's going to be a useful tool when we do the rest of the notes. Okay, so go ahead, take a little 5-minute break, and then come back and watch part 2 of the video. Have a great day, and I will talk to you later.